Welcome back to another lesson. This is basically part two of the whole lesson on electromagnetic induction. We're going to see the full scope of it now. In the previous lesson, we made mention of magnetic flux, magnetic flux linkage, right? And to be able to can see that whenever we take a magnet and induce it inside of a coil, right, such as a solenoid, what we basically see is that there's some amount of current that is induced, and if there's current flowing, it means that there will be a potential difference, also known as what we call EMF. EMF, as you would imagine, that is known as electromotive force. It's the same thing as what we call voltage or potential difference. Potential difference. It's the same thing. So, ladies and gentlemen, what I want you to understand about the whole aspect of electromagnetic induction, as the word suggests, induction, a charge, a flow of charge is going to be induced in a coil when a magnetic field is thrust in and out of it. Now, as you can see from this diagram here, we're going to watch it carefully. So, prior to moving the magnet inside, you realize that there were no reflection on the galvanometer, or what we call the voltmeter. But as soon as the magnet is moving through the coil back and forth, we're seeing that the needle is showing a deflection. When it is not moving, there's no deflection. So that is as a consequence of the fact that in order for a voltage or an EMF to be induced, a magnetic field has to be moving inside of the coil. All right? We're going to look at it and understand it from a great dimension to see what is happening and what did the scientists say about this. Now, to start off, electromagnetic induction, we're going to define it. It says that electromagnetic induction is when a current is induced due to a change in the magnetic flux linkage, right? It says that the current is generally induced in the wire by moving the wire through a uniform magnetic field or by varying the magnetic field strength. So there are two ways in which we can allow current flow. One is by moving the wire through a magnetic field or by varying the magnetic field. So when you look back at the animation just now, what we had there was the magnetic field changing across the wire. But what we're going to look at next is the fact that a wire is going to be moving in between the magnetic fields. But let's consider something here. The whole reason why the current is allowed to flow is because there are what we call delocalized electrons within the metal. All right? As you know about a conductor, right, has a lot of free electrons that will allow current to flow easily. So because you have free electrons inside of the conductor, when the magnetic field interacts with those charges, it will ultimately cause the charges to move. And if you can remember anything about the lesson about the force that is experienced on a charge, right, within a magnetic field, that force, as you should remember, that force is equal to F is equal to BQ times V, right? So what you're seeing here is this is essentially the force that is caused by the magnetic field. So if you have the wire, right, that has 3 electrons in it, placed within a magnetic field that is moving, or if you're moving the wire in the magnetic field, then you will be essentially allowing the magnetic force to actually move those electrons. So that is how the flow of electricity occurs, right, when the magnetic field is either moving or the wire is moving over the magnetic field. So this is an example of what we mean right here, right, of having the wire moving through the magnetic field. So if we were to set up a wire like this and have a meter connected right here, what you would essentially see is that as the wire is moved, and as a matter of fact, the wire here is moving perpendicularly to the magnetic field. So the magnetic field is going like this, and the wire is positioned at a right angle to the magnetic field. So that's a very critical thing to understand, that in order for this to happen, the magnetic field has to be perpendicular to the wire. So this is the wire. And the wire, as you can see, is positioned perpendicularly. What I mean by perpendicularly, they form a right angle. Now, what if my magnetic field was going up like this and my wire is like this? Clearly, no magnetic field is cutting across the wire. So hence, you would not have a current being induced in the wire. So this is the wire, right? What if that was the wire and my magnetic field was going up like this? Then it means that no current would be induced in the magnetic in the wire, and that is just due to the fact that the wire has to be positioned at a right angle to the magnetic field. So this is your B field, and this is your wire, basically, that will allow the current to flow like that. So in a sense, it has to be at a right angle, guys. All right, so that's something that we have to remember as well. And the reason why we put it at right angle is because at right angle, that is when the wire would essentially experience the maximum force. All right. Now, if you observe this carefully, you're seeing a little bit of graph being plotted here. This graph is just showing us that as we move the wire through the magnetic field, right, a voltage is being developed, reached to a maximum point. Then, of course, when you stop moving the wire through the magnetic field and bring it back, you can see that the direction of the current is now changing. So at first, the current is going like this when you're pushing it through the magnetic field, but when you're pulling it back now, the current is going in the opposite direction. That we're going to talk about, but it's just something for you to realize here. Now, we can use our Fleming's left-hand rule, right, to predict the direction of the current, right? We can use that, or not only to predict the direction of the current, but to also predict the overall force that will be experienced on the wire. So it says that from the diagram below, by using Fleming's left-hand rule, right, it says we can determine the direction of the force and, of course, the resultant motion, right, of the electrons. It says as the electrons move down, the induced conventional current produced is towards the left. And they're talking about this one, right? So here we have a magnetic field that is going across like this, right? So let's identify our magnetic field. If we identify our magnetic field, which is going across the screen like this, right? If we can imagine, let me see here, FBI, force is equal to B times I times L, right? I believe if we're talking about electrons, right, we should remember that the force that will be acting on the electron would be basically acting downwards, right? If we look at, a particular, if we look back at a particular diagram, then you would see that, generally speaking, when you have, electrons in the conductor here, right, what we would see is that those electrons would tend to, or the magnetic force would cause those electrons to be basically pushed downwards, right, causing the wire to be pushed downwards, and of course, then you would see that this is the direction through which the current would flow, right? Now, one other thing that we are going to realize here is that in the process of, so it says that when the direction is reversed, so that is the direction of the wire moving in the magnetic field, it says that the induced current is in the opposite direction, right? And it says that moving the wire back and forth with an oscillating motion will cause an alternating current. So when we think about the word alternating current, right, how alternating currents are made is by way of moving back and forth a, a magnet, not a magnet, but a wire rather, in between a magnetic field. So just as what you're seeing right here, this graph is essentially showing you what a alternating current looks like. The alternating current is current that flows in two directions. So let's imagine that we're going to talk about alternating current, but imagine that we have a graph here, right? And you start out the graph you start your experiment by pushing the wire through the magnetic field. As you push the wire through the magnetic field, essentially current is flowing up to a maximum point. Then the current is now going to decrease as you slow down the movement of the wire. Or not only that, but as you exit the magnetic field, as you exit the magnetic field, you come to this point. This point is where you basically would have stopped, right? And when you pull back the wire, as you are going to see now, when that wire is coming back, right, then you're essentially creating the negative portion of the graph, right? So that is essentially what is happening if you were to take a wire and pull it back and forth in between the magnetic field. It would ultimately create what we call alternating current, right? So alternating current is a current that travels in both directions, both positive and negative directions mainly, right? So we're going to look into this somewhat, right, to just get a better feel. So we have been talking about an EMF that is generated. Now, a famous scientist by the name of Michael Faraday, right? He went ahead and did a lot of extensive work as it pertains to electromagnetic induction, because he was not satisfied with the work that Oersted did as it pertains to understanding the fact that a current carrying wire would have created a magnetic field around it. So he understood that, but he then said, what if I were to take a magnet and move and allow the wire to pass through the magnetic field? When he did that, he realized that a small voltage was detected on the galvanometer, similar to this, right? So from his understanding is that, right, if a current carrying wire can create a magnetic field, then it means that we can create current by taking a wire and moving it through a magnetic field. So that's what he did. And when he did that, he realized that the voltage that was produced depend on several things. One of which, the voltage, depends on the change in magnetic flux. Now, magnetic flux, as we would have defined earlier on, it speaks to the number of magnetic field lines passing through a given area. That's what magnetic flux is. So imagine that we have the wire. That wire has a particular area, and if we're passing that wire through a magnetic field, then X amount of magnetic field line will be passing through the area. Hence, we can say that there will be a change in the magnetic flux, right? So the voltage here that he's talking about is dependent on the change in the magnetic flux, but not only the change in magnetic flux. He was able to say that the voltage is dependent on the rate of change of the magnetic flux linkage. So, in essence, what he's literally saying, the faster you move the wire through the magnetic field, it's the more voltage you're going to essentially get, right? So, when you think about generators and all those kind of things, the faster the turbine spins, is the more voltage you get. So in essence, that was his thinking about the whole aspect of, electromagnetic induction. And from that, he came up with a general equation that says that the change in magnetic flux linkage, or the rate of change in magnetic flux linkage, is directly proportional to the electromotive force, which is the same thing as the voltage. So if you see this, that says E, which speaks to the electromotive force, is equal to the rate of change of magnetic flux, right? But there's a minus sign in front here. Now that minus sign, we're going to talk about it. But I just want you to see that this is what we call the rate of change of magnetic flux. And this right here is directly proportional to E. So by way of moving the wire faster through the magnetic field, it means that it is cutting across the magnetic field much faster. When that happens, it allows more electrons to move much faster within the conductor, and hence you're going to have more electromotive force, right, being produced, or what we call the voltage. So more voltage will be produced, right? But you see, when it comes down to electromotive force, we generally use the formula that says E is equal to minus D of the magnetic flux linkage, right, divided by dt. Now another way you'll see it, and when I next slide you'll also see it. And a matter of fact, we can also write it like this, right? We can also write it like this. One of the things that you must understand is that magnetic flux is this symbol here. This is what we use to represent magnetic flux. But the thing about it is that it's magnetic flux varied, meaning that you can have several magnetic flux, right? So whenever we're talking about more than one magnetic flux, then we have to say magnetic flux linkage. Magnetic flux linkage, and that is basically N times the magnetic flux. So the N speaks to the number of turns, and you're going to see that coming out eventually, right? So if you see us writing that E is equal to minus D, we could say dN of this divided by dt. It's really the same thing. We could factor out the n as well, just as what you're seeing here. So not to create any confusion, let's just factor it out as what we're seeing on the board, because what we're saying now is that the EMF is the rate of change of magnetic flux linkage, not just only the rate of change of magnetic flux. If you say it's the rate of change of magnetic flux, you're still correct. But in some regard, it is a change of it's the rate of change of magnetic flux linkage, which we denote magnetic flux linkage as N times psi, or N times the magnetic flux. So this is the real way of writing it. That is the real way of writing it. We'll soon talk about the minus sign. Now, the minus sign does not affect the overall answer. It just shows us something very important. We'll soon talk about that. Well, another thing now, let me see if I'm forgetting anything here. Okay, yes. Don't be confused if you're seeing d psi and dt, right? That just really means anytime you see that, if you're seeing the magnetic flux, it means the change in magnetic flux. If you're seeing dt, it just means a change in time. Okay, and another way you'll see us writing this overall equation, you're going to see it on the next slide, but I want to just show you from here. Another way you'll see that is by saying that the EMF, which is the voltage, the EMF which is the voltage, is equal to minus delta magnetic flux divided by delta T. So anytime you want to calculate E, right, which is the electromotive force, there are several ways we can calculate it. This is one way, right, by finding out what is the change in the magnetic flux and what will be the change in time, right? There are some things that we should recall as well. There are some things that we should recall, and one of that is that magnetic flux, magnetic flux, which is this, is equal to the magnetic flux density times the area. So we could essentially rewrite this to say that E is equal to minus the rate of change of B upon dt. We could have rewritten it as such, because as we said, that magnetic flux is basically the magnetic field strength per unit, not well, it's the amount of flux line that is passing through a given area. So you know, if we wanted to calculate E, then all we would need is this, all of this information here. We need to know B, we need to know A, and obviously we need to know the time, right? And from there we can find out the information, right? This is what I was talking about as it pertains to you seeing the triangle. The triangle means change, right? The triangle means change in. So it's the same thing as the thing that we had that says D, right? D magnetic flux is the same thing as saying the change in magnetic flux. And if you're seeing that sign, that triangle, it also means delta. Delta. So delta psi, or delta magnetic flux, right, means a change in magnetic flux. Nothing to worry about, because those are not like a number or anything. It's just showing you, it's just a symbol to denote that there's a change in the magnetic flux. So what it's just really telling us is that the faster you move the magnet through the magnetic field, it's the more EMF, the more voltage that will be produced. All right. Now, the whole reason for the negative sign here, we're going to talk about it now. Right? The whole reason for the negative sign is to tell us that the current that is induced in the wire, that current is going to essentially be in the opposite direction, or it's going to flow in the opposite direction to basically produce a change that is causing the induced EMF. It's a little bit not so easy to understand, but I believe that you're going to understand it. So here we are saying now that it says Lenz's law. So Lenz found out some information. So his law states that the induced EMF is generated in a direction so that it opposes the change that is causing it. And we're going to look at it. It says, therefore, if the wire is pushed down into the magnetic field, the current in the wire will be in a direction that produces a force to oppose its motion in the I think this is supposed to be magnetic field. Okay. Now we can use Fleming's left-hand rule right here to predict, you know, the overall current. It says that this will produce a current by the Fleming's left-hand rule, which will cause the wire to be forced upward. All right. That was just speaking from a wire standpoint. Another thing that we must remember about Lenz's law is to the fact that Lenz's law is based on what we call a conservation. It's as a consequence of what we call the law of conservation of energy, right? Because what you're seeing now is that when the magnet is coming towards the wire, right? As you can imagine, the wire is essentially going to do work against the the not the wire but the magnetic field will be doing work, right, to move those electrons. Now, as you can imagine, an EMF is going to be produced. So what we're seeing here is that by as because you're moving the magnet towards the coil, that moving is basically using up some amount of energy. So moving the magnet towards the coil is converting that movement of that energy that's associated with the movement into electrical energy. So he says that if you can move, right, a wire into a magnetic field of a horseshoe magnet and generate an EMF, then an electrical current has to be produced within the wire. But where does this energy come from? That's a very good question. Where does that energy come from? Right? That energy is really as a result though of the fact that the magnetic field is doing work, right, against those electrons. And I mean, if they're doing work against it, then it's going to cause an electric current. So energy is being conserved at the end of the day, right? So that's another concept that we have to remember about Lenz's law, right? This is just explaining all of what is happening here, right? Because we said a while, we made mention of Lenz's law, right? Which is just telling us that when an EMF is induced inside of a coil, right? The coil is going to basically generate a current so that it opposes the flow or it opposes the change that is causing it. So imagine that we have a magnet and we're pushing the magnet into this coil. If we know anything about the coil, right, a coil is almost, let's just imagine that this is just a portion of a solenoid, and we know that for a solenoid, it's almost like a magnet, so to speak, right? So if I'm taking my north and pushing it towards the coil, what the coil is going to automatically do, it's going to allow a current to flow in the wire that would generate a magnetic field that would oppose the magnetic field that is coming towards it. So if we look at this, and for us to understand this, we have to use our Fleming, well not Fleming, we have to use our right hand grip rule to kind of understand what is happening here, right? If we know anything about a coil or a solenoid, right, we use our fingers to represent the flow of current. So what we're seeing here is that by pushing the magnet, this magnet towards the wire, as that magnetic force comes towards the wire, the electrons in the coil is now going to start moving over the coil like this. It's now going to start moving over like this. And if we check a step, if we take our right hand, what you would essentially see is that a magnetic field will be generated, because remember now, whenever there is current flowing in a wire, there is a magnetic field that is generated. So this is what is essentially happening. So because there is a what would you call it now? Because the current is now flowing over like this, right? Then what you would see is that the wire is going to produce a magnetic field that will oppose the change that is causing that current. So it's just opposing it, right? But for how long can it oppose it? But another thing that we must understand, it says that if we try to increase the flux, right, through a loop, the induced field will oppose that increase, right? So the more we try to increase the loops, right? If we increase the loops, we are basically increasing the flux that is going to be in the wire, but it also will present that there will be an increase in terms of the opposition as well, right? Now, another thing that we're seeing here is that what if I were to pull away the magnet, right? So after pushing the magnet through the coil, and you now want to pull it away, right? Now remember, if the wire, let me see here. Give me a second. Yes. So let's see here. So if I want to pull away the magnet from the coil, so at first I would have pushed the magnet towards the coil. I realized that the the magnetic field around the coil would have opposed it. Now the way how this thing works is that after wanting to pull the magnet, so after pulling the magnet out of the coil, what we're now seeing is that the coil is going to almost want to keep the magnet inside. So what you would realize now is that the moving of the magnet away from the coil will allow the current to flow in such a direction that it will uh, oppose, not all, in this case, it's not going to completely oppose, but it's going to want to keep the change that happened at first. So what you would see is that the magnetic flux is going to change, right? The magnetic flux is going to change so that, and that's the magnetic flux around the magnet, around the wire, I should say, that is going to change to essentially create a south pole. So when it creates that south pole, it's almost like wanting to keep back the magnet towards it. So one other thing about the coil is that it is a funny looking thing, meaning that at first it did not want the change. It wasn't accepting the change, but as soon as you're now trying to pull the magnet away, it is now telling you, hey, I want the change. I'm accepting it. I don't want you to go away basically. So for it to prevent the magnet from going away, it is now creating a south pole to attract the north pole. We're going to look at another diagram in a sense which is somewhat more better to essentially see and understand. And we have to be able to can describe these things in a sense, or not only describe it, but you will see questions like these, right? So at first, this is your north pole of the magnet that is going towards the coil. This is a solenoid, I should say. So what you would see now happening is that as you push the solenoid into the coil is going to allow a current to flow in such a direction that this end of the coil is going to be a north. This end of the solenoid is going to be a north pole. Because as you know, whenever current is flowing through a solenoid, it creates a magnetic field around it. And so what we're seeing is that as the external magnetic field moves in, it's going to allow the current to flow in that direction, right? And with that being said, we're now seeing that by way of using the right hand grip rule for solenoid, right? And remember, for the right hand grip rule for solenoid, we said that the four fingers represent the direction of the current, and the thumb represents the direction of the magnetic field. So by using that, we're seeing that the current is flowing down like this, and the north pole is automatically going to be like this, because you're opposing the change that is coming towards you. So this is another scenario when we now pull the north pole outside or out of the solenoid. In the process of pulling the north pole out of the solenoid, what we're seeing essentially is that the current in the coil, right, is going to flow in such a way that it opposes, well, not opposes, well, there's two ways we can look at it. There's two ways that we can look at it, right? There's two ways that we could look at it. Yes. But at the end of the day, it's going to essentially create a south pole on this side. Going to create a south pole on that side, right? On this side to essentially basically keep back the magnet inside. Let's just draw a bar magnet for argument's sake. This is a bar magnet. And we know a bar magnet has a north and a south. Alright? Let's imagine that the bar magnet the bar magnet is completely inside. Let's imagine that the bar magnet is completely inside. Trying to see if I can use some different colors here to just allow us to see what is happening. I'm not sure if that one will work. So let me see if I can use the white. I don't know if this will work. Alright, let me try something else here. What I want you to see, because there's, as I said, there are two ways we can look at it. Right? There are essentially two ways that we can look at it. Alright, I think the highlighter could. Alright, give me a second here. What I want to create is a bar magnet. Here's a bar magnet. So this is when this is the north, this is the south. So at first we would have pushed the bar magnet inside of the solenoid, right? And you would have more than likely pushed it all the way until it reaches outside here. Right? So you'd have automatically pushed it until it reaches outside here. Right? Now, for this scenario here, here's our magnet, right? We are now pulling the magnet in this direction. We're now pulling it in this direction. Now, as you can see, this south pole is going towards this end. The south pole is going towards this end. So what we're seeing is that this south pole is going to be opposed, right? It's going to be opposed. The coil or the solenoid would essentially be creating a current to oppose it from coming through. So that's the reason why we say that this side is essentially going to be a south side, because the coil is going to allow the current to flow in such a way that it is now going to essentially prevent the magnet from it's going to oppose the change that is causing it. So at the end of the day, it is creating a south pole here to basically prevent this south pole from creating a change in a sense. So that's kind of like what is happening there. It's not completely easy to understand, right? But what I want you to get is this. Whenever, for you to get this, one of the things that you can use to remember, right? You see, whenever the current, not the current, but whenever the magnetic field is moving towards, so whatsoever side of the magnet that is moving towards the coil, right? Whatsoever side of the magnet that is moving towards the coil, okay? So if a north side is moving towards the coil, then at first it's going to be opposed. So just think about it being opposed, right? But now whenever you're moving the north away from the coil, a south pole is generated to prevent the magnet from moving away. So it wants to keep it inside. It wants to keep it closer to itself. So it's going to generate a south pole. So at first it never want to change, right? And then now, as soon as you allow the change to occur, it is now wanting to keep it. So always remember that. we can look at it from a south pole standpoint. What if I take a south pole and I push it towards the coil? What you're going to see is that the current, right, that is going to flow in the coil is going to ensure that a south pole is generated right here. And how do you know that a south pole is generated right there? Is by way of using your right hand grip rule for solenoid. So if you use your right hand, you will see that the current is going up like this. Your current is going up like this, and obviously your magnetic field is pointing out like this. So that is what is happening there. Now, what is happening in this one? This one now, whenever you're moving away the south pole, the solenoid is going to essentially create a north pole by changing the way how the current is flowing, so that it can keep the south towards keep it close to it. In a sense, it does not want to allow the south pole to go away from it. So it is now creating a north pole to essentially keep that in closer to it, right? So it's a lot of things going on as it pertains to Lenz's law. Now it says that when the north pole of a magnet approaches a solenoid, it says an EMF is induced in the solenoid. It says that the induced current in the solenoid flows in a direction to produce a north pole to oppose the motion of the magnet coming towards it. Now it says that when a north pole moves away from the solenoid, an EMF is induced in the solenoid. This time, the induced current in the solenoid flows in a direction to produce a south pole to attract the magnet moving away from it. So that is just what is happening there. So once you know what is going towards it, if it's a north pole, you know that the first end of the solenoid would be a north. And if you're moving the north pole away from it, then it means that that end where the north pole is moving away from is going to be a south, because the coil or the solenoid wants to attract back the north pole towards it. So that's what is happening, right? But what I want you to understand is that while we're talking about the wire and everything, it's really the electrons inside of the wires that are actually behaving in a particular way. They are the ones that are actually moving. So just be mindful of that, right? Those are the ones that carries the charge, and they will determine how the wire will move and all of that, right? We're going to move into something else here just to quantify the electromotive force or the EMF that is generated in a piece of metal, right? That is it's movable in a sense, because if you look at this, here we have a piece of wire and a piece of wire right here. It's almost like a rail track in a sense, where we have this piece of wire that is not connected, but it is able to touch against the other rails, and obviously these rails will have a current flowing through it, right? So what we're going to see here is that by essentially allowing this wire to be inside of a magnetic field, then based on the electrons inside here, those electrons would essentially experience a force, right? And that force that it will experience will tell us what direction the wire, this piece of wire, will move towards, okay? But before we do that, we're going to talk about it here, just to let you see something here, right? There's not one equation whenever we're trying to find something, right? So what we want to do now is to sort of like prove an equation of whenever we want to find the EMF that is induced in a particular piece of wire, right? That is placed within a magnetic field. And as a matter of fact, this wire here is going to move. So at first, let's imagine that a current is flowing through the rod, for argument's sake. Now if a current is flowing through the rod, it's going to flow all the way around here, and it's going to flow all the way through this piece of wire. Now we can use the Fleming's left-hand rule to determine where this piece of conductor is going to move towards. So if you use your Fleming's left-hand rule, so firstly your magnetic field is going into the paper, so your first finger should be pointed into the paper. Then you should identify that your current is going up into the air like this. So your second finger should be pointing towards the ceiling. Then your thumb automatically is going to point towards this side. So we know that is the force that will be experienced on the wire. So by thinking about right, the overall force, that force is equal to B times I times L. And what we're doing here is deriving an equation for the EMF. We know from day one that E is equal to minus D of the magnetic flux times this. We know that information already, but now we are now dealing with this from a wire standpoint. All right, that is when a current or a conductor is placed with or it's moving through a magnetic field. Whenever that is moving through a magnetic field, we definitely can determine and see where the EMF is going to be induced, or how is it going to flow in the wire, right? But as you can imagine, right, in order for the wire to move, it's as a result of the magnetic force that is causing the wire to move, right? And if the magnetic field is doing work, right, to move the wire, then we can find the work by saying work is equal to force times distance. And that is like baby knowledge right here. We know that is the work. So first we started out with this to say that force is equal to B times I times L. So this is the force that is causing the work. And that work is being done within a particular distance, meaning that it's going to move the wire to a particular distance. Now it says that in this situation, the work is done in moving the wire through the magnetic field and is converted into electrical energy by doing so. So remember now, if the magnetic field is doing work, remember energy cannot be lost. So that energy that was used to be doing work is going to be converted into electrical energy. And that is the electrical energy that we are considered about. But from an electrical standpoint, right, we should remember that work is equal to Q times V. Or if you remember what potential difference speaks to, potential difference, right, is equal to the work done per unit charge. It's the work done per unit charge. And by just remanipulating this, you would have found out that the work that we're talking about here, which is force times distance, that work is being converted over to electrical work, which is now Q times V. Now, since we're talking about charge, we can see that charge is equal to the current times the time. Right? So by having that information, we can now do two things. One, let me go back here and show you what we'd have done. Right? I'm going to show you. So since we know that work is equal to force times distance, and the force right here is F times I times L, then I can say that the work is equal to B times I times L. I think I said something here that F is equal to B times I times L. All right. So that is the force times X. So this is my work here. That is the electric field, the magnetic field rather, is essentially doing on the wire. But as we said now, that work is going to be converted into electrical energy. And electrical energy which is what we call W, is equal to Q times V. Now, if I equate both things, if I rewrite this, by the way, if I rewrite work as I times T times V, where V right here is the voltage, that is the voltage that we're trying to prove right here, by the way. So be mindful of that. So now my work, because I know Q is equal to I times T, then I could replace that and I would get V, not V, but W, which is the work, electrical work, is equal to I times T times V. Now, by putting them together, so the two work equations, if I put them together, parallel together, let me see here. If I put them together, yeah, essentially. So if I put them together, this is what I get. So we're just equating both things. So B times I times L times X is equal to IT times V. All right. But we can see here that I is going to cancel out I. And then we want V to become the subject. So when V becomes the subject, it means that I now have B, right, times L, okay? And L, by the way, is the length of the conductor, right, times X divided by T, which is now equal to V. So my EMF that is now induced in the wire is given as this. But then, because we know that X, which is the distance that the thing traveled, so the wire is going to travel to X distance. So imagine that the wire moves to this point. That distance would be X, and within that movement to this distance, then we can also record the time. So at the end of the day, we can find the velocity of the wire would have had. So X upon T is equal to V. So we could have replaced that now to say B times L times small v is equal to capital V, where that capital V, right, is essentially what we call the EMF. So for a particular piece of conductor that is placed within a magnetic field that is being moved by the magnetic field, then it means that the EMF that will be produced is going to be B times L times small v, where V is the velocity, right? B is the magnetic field, right? And L is the length of the conductor. So this is just a proof, another equation that we could have used to find the EMF, all right? Having said all of that, that what we looked at a while ago was just for a piece of wire. What if we had a disc, a metal disc, that is moving inside of a magnetic field? As you can imagine, that there will be an EMF that is going to be induced in the what would we call it, in the disc, right? And for that reason, we could essentially derive an equation for that EMF. So what we would start out with is Faraday's law that says the EMF induced is equal to the rate of change of magnetic flux linkage, right? And if we remember, so seeing that E is equal to the rate of change in the magnetic flux linkage, right? Then we could see one or few things happening here, that D, not D, but magnetic flux linkage, right? Magnetic flux linkage can be rewritten as B times A, because we said that magnetic flux, rather, this is magnetic flux, not magnetic flux linkage. Magnetic flux linkage is when you have the N involved. So this is magnetic flux, right? So we could have rewritten it as this, divided by dt. Now, because we are looking at a disk, right? It's a circular thing, so we can find the area of it. So the area of the disk is pi r squared. So you could have replaced that information in this equation now to say that E is equal to delta um, B times pi r squared, right? Divided by d upon t. We could cancel out the d's. We could cancel out the d's. When we do cancel that, we are now left with that E is equal to B times pi r squared divided by t. We could rewrite this as to say 1 upon t is equal, 1 upon t, so E rather, E is equal to 1 upon t times B times B, which is the magnetic flux, times pi r squared. But then if you can recall something, so by way of recalling, frequency is equal to 1 upon t. So we can now see that if we wanted to find the EMF that is is um is ultimately you know, is ultimately induced in a disk, then EMF E is equal to the magnetic flux, well, not the magnetic flux density, right, times pi r squared times F. So this is what you would do whenever you have a disk rotating in between a magnetic field, right? So note the two differences in the equation. So one equation is for when you have a wire that is moving inside of a magnetic field, right? We said that that equation E is equal to B times L times V. So you would need to know the speed that the wire is moving, right? And you would need to know the length of the wire, and you would need to know the external magnetic field, right? In order to be able to can find out what would be the induced EMF inside of the wire. So that is pretty much what it's saying here. So this is for the wire. This is for a disk. Now, there are various applications as it pertains to electromagnetic induction, and I mean, we can't get away from it, right? I mean, right now, a lot of the things that we're using is incorporating electromagnetic induction. When you think about a motor, when you use a fan, right? You know, when you think about a wind turbine, all of those things are essentially using the whole concept of electromagnetic induction. There are several advantages of using things like these. And when you like think about the wind turbine, if we did not come up with the whole idea of electromagnetic induction, then we would not essentially be using wind turbines to produce energy up to this day, right? So it's important that we understand it. So at first, you will hear us talking about a generator, right? And a generator is a simple application of electromagnetic induction. It says, according to Faraday's law of electromagnetic induction, it says when a coil is rotating in a magnetic field, right, and EMF is induced, it says that the magnitude of the induced EMF depends on the speed of rotation and the number of turns in the coil. So there are several things that comes into play when we're dealing with a generator. So if we have a coil, you see, you're going to see it very soon. right? But if we have a magnetic field right here, this is my, you know, for argument's sake, all right, let me not use that one. But imagine that this is a magnet, a north right here, right, and a south right here. And you have a wire, so let's just draw our magnetic field. That's how your magnetic field moves from north to south. And if I have a wire, guys, and also you have to always remember that the wire has to be perpendicular, perpendicular to the magnetic field. So imagine that this is the coil of wire, for argument's sake, right? Now, if this wire is moved inside of the magnetic field, we said it already, but if you have the wire that is moving inside of the magnetic field, right, what you're going to see is that by moving the wire faster in the magnetic field, you would essentially be generating more EMF. And that's a beautiful thing. That is a beautiful thing, right? So we are going to see how best, and not only that, it says that the more number of turns that you have, meaning that the more wires you have in the coil. So this is like another wire additional here. What you would see is that having more wires would also increase the the EMF, because when you look at this equation, E is equal to, right, minus N times D times psi divided by D upon T. So in essence, the more N you have, it's the more E you're going to have. The faster you change this, because this is the rate of change of magnetic flux. The faster you change that, is the more E you're going to have, just the same way. Remember, the negative is just talking about Lenz's law. Please remember that. So you don't have to incorporate this when you're doing a calculation. You don't have to incorporate the negative, right? But the most important thing is to remember that the negative is there for a reason, and it is just to show the direction of the induced current. So in essence, this is just speaking about the EMF that is generated here, and we're not going to look at this. So as you can imagine, a generator, you see, is a device that generates or gives off current. It makes current in a sense, right? Or it makes voltage, and it makes alternating current, which means that it depends now on where the system is located. It depends on how the wire is positioned in the system, right? Depends on how the wire is positioned in the system here. Now, if the wire is perpendicularly, it's placed perpendicular to the magnetic field. And I must let you know this, by the way. A generator works or it rotates by mechanical means. So for you to turn the coil inside of the generator, think about the wind turbine. It's the wind that is turning the coil inside of the magnetic field. So that is something that you must remember about a generator. A generator it operates based on mechanical energy, where somebody has to turn the coil inside of it for it to generate energy, or something has to do it, right? Before energy can be created. So, but in the process of doing that, what we're essentially seeing here, that if I'm turning the coil inside of the magnetic field, by turning it into the magnetic field, there will be points where the wire will be cutting against the magnetic field at a right angle. And at this moment, that is what is happening here. So based on how this coil is positioned, the wire right here is placed perpendicularly to the magnetic field. So that is when it's going to experience its maximum force. So there are several things that are occurring, right? So as you can imagine, let's imagine that current is flowing through the coil, right? Now, by using Fleming's left-hand rule, this is where your magnetic field is going, and if you know where your current is flowing, so your current is flowing like this, going into the board, then what you would essentially see is that on this side of the wire, there will be a force acting down. There will be a force acting, let me see, would it be acting down? Let me just verify this again. Oh, so no, it's not the Fleming's left hand rule, it's the Fleming's right hand rule, my bad. It's the Fleming's right hand rule. So Fleming's also has a right hand rule. The left hand rule wouldn't work in this case. So you have to then know when to use the Fleming's left hand rule and when to use the Fleming's right hand rule. So the Fleming's right hand rule would work in this regard, right? Where we can, it's the same thing in terms of the position where your thumb represents the force, your first finger represents the magnetic field, and your second finger represents the current. So because the current is going into the board and the magnetic field is going across, let me just correct something here, because what you're going to see is that the rotation, or that the force right? So as I was saying, that current is flowing into the wire and your magnetic field is going across like this, then what you're going to see now is that there will be a force acting up on the wire. There will be a force acting up on the wire. So by using the Fleming's right hand rule for the generator, then you would automatically see that your thumb is pointing up. So once you have located your magnetic field going from north to south, and the fact that you would have realized that the current in the straight piece of wire is going into the board or into the paper, right? Then you would see that your thumb is pointing up. So what it tells us is that the wire is going to move up into the ear. The wire is going to move up into the ear. But let's consider what is happening on this side. Let's consider what is happening on this side of the coil. So on this side of the coil, our current is perpendicular to the magnetic field, right? Which is wonderful because that's what we want. Now, using the same Fleming's right hand rule, find the magnetic field which is going from north to south, then find where your current is going. My current is going towards me in a sense. Let me just ensure that my hand is positioned correctly. So your your middle finger is pointing almost like towards you in a sense, right? And of course your thumb is going to be pointing down. Your thumb is going to be pointing down. So what we're seeing, how the generator works now, is that once current is flowing through the wire, right? Then at this point, it's going to experience a force pushing it up. But on the same time, the other side of the coil, right, is going to experience a force downwards. So it's going to do that, right, until the coil is positioned in an awkward way. But I wish I had the diagram to show you. But the coil is no longer going to be like that. It's going to be like long way. It's going to be like long way like this. So this is like how it's going to look. No, it's going to basically be up in the ear like that. But I'll show you in another diagram, hopefully. Right? So yes, this diagram I think could explain it. So when you look at this now, this is what would happen after you consider the fact that the wire is now positioned like this. If the wire is now positioned like this, then what it means is that no magnetic field will be able to cut across the wire, because the wire is no longer within the magnetic field. So the wire piece, that piece of wire that was perpendicular at first, is no longer perpendicular to the magnetic field. So it's not able to cut across. As a matter of fact, this is an alternator. My bad. But either way, it's the same generator. But, no no magnetic field is cutting across the wire. And if there's no magnetic field cutting across the wire, then it means that there will be no force. So when you look at this progression of the graph here, we are seeing that when the wire is like this within the magnetic field, so the dot here speaks to the magnetic field, right? That the dot is passing through. As a matter of fact, yeah, the dot means magnetic field coming out, by the way. So that means magnetic field is coming out. When the magnetic field is coming out towards you and the current is flowing into the coil like this, that is when you're going to have maximum current flowing. That's when you're going to have maximum current flowing through the coil, because you essentially have maximum force acting on the wire. But as soon as you're now positioned like this in terms of the coil, then that is when you will not have any current flowing through the wire, because there's no force that is being acting on the wire, right? That's when there's no force acting on the wire. And so it continues like this, where, when the wire, because what's going to happen is that when the wire is in the ear like this, right, it's still going to have a momentum that is going to bring it back to this point. So even though there's no force acting on it, it still has a momentum that is going to cause it to move to this point or come back to this point, where it can now experience a force and then generate current again to flow through the wire, and it continues its cycles there and there. This is just a breakdown, right, as it relates to an alternator. Is the same thing as a generator, right? It generates current, right? So it's something that we should also be able to just catch it in a sense, to show that this is what it looks like and how it works. There's what we call some split rings right here, split rings, and of course there's a contact brush. These contact brush is essentially what is collecting the voltages. So as you can see that these two coils, right, one split ring is connected to the voltage on the red side. So if you're observing this correctly, what you're seeing here is that yes. So what we're essentially seeing is that this red piece of wire is connected, or it's brushing against this ring. Okay, and as a matter of fact, this blue is not connected to the first ring that you're seeing here. So as the rotation occurs, right, based on the current that is flowing through this piece of wire here, right, it will, essentially give us a particular current, right? And of course, the blue wire here, which is connected to this first ring, right, depending on what the voltage is or whatsoever the current is in this piece of wire, then we will essentially get a reading, right? And of course get a overall voltage. But mind you, there's what we call a carbon brush. A carbon brush is just a piece of, material that is made up of carbon, that is able to run against or touch against the coil as the coil rotates, as this ring, I should say, rotates. With this type of alternators, it does not use a split ring. Well, the reason why we call it split ring is because you have two separate rings, but in some others you will see a complete split ring, meaning that it is divided, right? And that's for the DC generator when we look at it. All right. So this is just kind of like, giving us a better example, or working out as to what is happening at each point of the system, right? Where you can look over that and just get a better feel of it and to see what is happening there, as the system, when the wire is positioned at different angles. All right, so we want to take on this quick question here. It says that figure 21.11 shows a copper disc which is spun in a magnetic field at the center of a long solenoid. It says a sensitive voltmeter is connected between the brushes that make contact with the axle at the center and at the rim of the disc as shown. It says explain why an EMF is detected by the voltmeter. B, it says um, the solenoid has 200 turns per meter and carries a current of 0.5 amps. Calculate the flux density at the center of the solenoid. So the first question would be for us to say why there is an EMF that is detected by the voltmeter. So as you can imagine, remember now that a solenoid, as long as current is flowing through the solenoid is going to generate a magnetic field. Follow me? And with that being said, if you have a disc that is spinning inside of the magnetic field, then essentially you're going to cause electrons in the disc to move, and as a result, current would be flowing, right? So it says that a voltage is detected as a result of the movement or the rotation of the disc inside of the magnetic field. As the disc rotates, the magnetic flux linkage is changing with time, and as this occurs, an EMF is going to be developed. So you can come up with your own answer just the same way to just explain it, right? But just remember, as long as you have a conductor that is rotating inside of a magnetic field, there's going to be a change in the magnetic flux, and whenever there's a change in magnetic flux within a particular time, then that will now tell us that there will be an EMF that is going to be produced. So it's all related to electromagnetic induction, just the same way. Now the question moves on to ask us now to find the magnetic flux density. Now remember now that the magnetic flux density for a solenoid is equal to mu naught times I times N, where mu naught is equal to what we call the permeability. Permeability of free space. And then now that's mu naught. Then now N is what we call the turn density. Which you should remember that N is also equal to the number of turns per unit length. So once you see 200 turns per meter, that's talking about the turn density. And obviously I is the current flowing through the coil. So we can go ahead and find B, which is the magnetic flux density. We know that mu naught is 4 pi times 10 to the minus 3, 10 to the minus 7, right? We're now going to multiply that by 2000 times 0.5. Having said that, by working out the calculation, then we can see that the B field is going to be 1.26 times 10 to the minus 3 Tesla. Tesla is the unit for magnetic flux density, right? Having said all of this, the question continues to say that the disk radius is 30 millimeters and it spins at a rate of 400 revolutions per second. Then it says that by considering the motion of the radius of the disk, right? It says calculate the magnetic flux that cuts through per revolution. So they're asking us to find the magnetic flux, and we know magnetic flux is this thing that says B times A. So we want to know the magnetic flux that is cutting across the area of the disk. So this is the diagram. This is the disk inside here. That's the disk. That disk is rotating. So here's a motor that is rotating the disk inside of the magnetic field. And of course, by rotating it, then we can clearly see that there will be a small voltage that we can record on that disk. So we just calculated the B field a while ago. But because it's a disk, we know that the area is going to be pi r square. They told us all of this information already, so we can just go straight ahead and find out that information. So our change magnetic flux is now equal to 1.26 times 10 to the minus 3 times the area, right, which is pi times the radius square. So that's going to be 300 times 10 to the minus 3 squared. When we do work that out, we're essentially, let me just see something here. Yeah, so once we're able to do that, just give me a second. So let's just put it together. So 1.23 e to the minus 3 times pi, then times, all right, I think I'm getting that the magnetic flux is going to be 3.56 times 10 to the minus 6, right? I believe that's the answer that we're getting. Yeah, I think so. Then now the question asks us now to find the rate, right? So calculate the rate of change of time as at which the magnetic flux is cutting per second. Yeah, so we could essentially find that out. So that is the rate of change. Yes, let's see here. Right, so dt, not dt, but d magnetic flux per dt is equal to, as we know, if time is 1 second, right? Essentially, we're saying that, you know, remember now that remember that magnetic flux is B upon A divided by dt. So this is just telling us that our change in magnetic flux, right, within 1 second is essentially saying B times the area divided by 1. So our change in the our rate of change in magnetic flux um, is essentially going to be the same thing right here. It's going to be the same thing because you're just saying 3.56 times 10 to the, as a matter of fact, that was 10 to the 5, by the way. 10 to the 5. So minus 5 Tesla divided by 1 second, because you're just considering for 1 second what would be the overall rate of change of magnetic flux per second. So this is essentially what this is, right? Then of course now, if it asks us to find the EMF, right? If it asks us to find the EMF, I think I could have looked at this differently, I think I could have looked at it differently. because what you would see is that what you would essentially see is this, to say that, um, d of the magnetic flux to dt is actually saying um, b times a times the frequency. That's what it's really saying. So I think we should clarify that here. So our frequency is going to be 40 because it's saying 40 revolutions per second. So remember that frequency speaks to the number of revolutions per second or per unit time. So in this case, we can just simply say, all right, um, this number here, so it's 3.56 times 10 to the minus 5 times the frequency, which is 40. When we do that, we are getting a number of, to say that our rate of change, right, of magnetic flux density within, per second is really equal to 1.42 times 10 to the minus 4 Tesla, right? So at the end of the day, what we should understand though is that this rate of change of magnetic flux is the same thing as what the EMF is. So the EMF that we are going to find now is essentially equal to the rate of change of magnetic flux per unit time. So our EMF is really equal to 1 point, by the way, this is not Tesla. This is actually volts, right? That's actually volts. So having said that, at the end of the day, this is what we are saying here. Or we could even look at it from the standpoint to say that E is equal to B times A times frequency, right? Because that's what we just did over here a while ago. Okay, so having said that, we are now saying that your magnetic field, magnetic flux density times the area, where our area is pi r squared times the frequency. So at the end of the day, this what we calculated over here is essentially the same thing. So that rate of change of magnetic flux is the same thing as the EMF that is induced, which is going to be 1.42 times 10 to the minus 4 volts, or we could bring it to millivolts, right? So if I move the decimal point to the right one time, I have to, well, not to the right. If I move it, I have to move it to the left, and then I'm going to plus 1 to the power. So let me just fix that. So if I move the decimal point to the left, I now have it to say that E is equal to 0.0142 milli millivolts. I could just verify if this is correct. I think it's not correct. It's going to be 0.1, 0.1, not 0.01. It's going to be 0.1. It's going to be 0.1, 0.1. Yeah. If I put in 0.1 for 2 e to the minus 3, yes. So it's going to be 0.1. At the end of the day, this is the amount of EMF that is generated across the disk when it is rotating within the magnetic field. All right. Now just read up this information about DC motors and see how it works. All right. Then from there we're going to move on to something else. So this comes to the end for this particular aspect of the lesson.